Well, again, thanks a lot. Thank you very much for inviting us here. My name is Neil Goldsman. I'm with the company CoolCat Electronics, LLC. I'm also a professor at the University of Maryland in College Park. CoolCat Electronics essentially spun off of some work, essentially a group at University of Maryland, and we've been around for about 6 years, aggressively around for 6 years. So, okay, so what is CoolCat? CoolCat is a startup. It has 3 major technology areas. The first area is silicon carbide-based electronics. And in this area, we do design, fabrication, and development of silicon carbide-based devices, wide bandgap semiconductor. And one of our key programs is silicon carbide photodiodes and avalanche photodiodes, specifically funded by NASA. We also do a lot of computer-aided design work, which helps us to build these unique devices. And we also do prototyping for instrumentation. Trying to advance this. How do I? Okay. Okay, so CoolCat was formally established in 2006 with a postdoc and myself, who was my partner. And since we ramped up in about 2009, and since then we've had 16 employees. We currently have 16 employees. In 2004, we had 1.4 million in revenue, and mainly, that revenue is mainly from government and some private, and the type of business is an LLC. Most of the employees are technical, although we have one or two, one administrative type employee and one business development employee, which are also key. Okay, most of the employees are, at least half the employees are PhD level. Other half are scientists of, sort of learning scientists in the sense at the master's and bachelor's level. And every so often we get student interns from the University of Maryland, since we are located about a mile from the University of Maryland. Okay, so for this particular presentation, I'll be talking about silicon carbide deep electronics, and specifically ultraviolet optical sensors, photodetectors. Okay, photodetectors and avalanche photodiodes. So avalanche photodiodes is actually sort of an application of a photodetector. The technology ready level for this program is mid-range. It's about a 6. Okay, so in terms of uniqueness of this program, well, it uses silicon carbide wide bandgap semiconductors. Essentially, silicon carbide being a quasi-new material, which really is just now coming into its own, has the advantage that since it's wide bandgap, it is solar blind. It is essentially visible light blind. So it's transparent to visible, but absorbs UV. And at the same time, since it is a wide bandgap semiconductor, it has extremely low noise levels. And since it, well, trying to get back. Okay, and since it has these low noise levels, we can actually get to the level of counting or detecting a single photon. In order to do silicon carbide, well, it has these benefits, but at the same time, since it has these benefits, it's very difficult to process. And so the process, the fabrication steps that we've developed are unique, and that's part of the state-of-the-art of this development. Okay, so what do we have here? Okay, I don't know why. Okay, so a little bit of background. Okay, so what is okay, so what is a photodetector? Okay, well, I think probably most of us know, but here is a UV photon coming, a single photon coming in, and here is essentially our photodetector, largely a type of PN junction. Okay, well, the PN junction is made of silicon carbide. It is designed very carefully with very specific doping levels, gradients in doping, et cetera, in order to be able to detect this single this UV photon. At the same, why do we have to be careful about that? Well, high energy photons, they have the tendency to, you generate an electron hole pair on the surface, and that electron hole pair will quickly recombine. So it's very hard to actually get a signal out of a UV detector. Or out of a deep UV detector. When I say deep UV, I mean about 200 nanometers in light. So you have to be very careful about designing the doping profile. At the same time, silicon carbide is very hard to process, so you have to be very careful about how to eliminate traps, surface states, et cetera. Then finally, if you want to detect single photons, and where our previous speaker was talking about channel plates and things like that. Well, if we want to detect a single photon or a single particle, we run this in some kind of avalanche mode, and where a single photon comes in, that single photon then generates, due to avalanching, 1,000 or even 1,000,000 electron hole pairs, and then you get pulses out of it. Then you count you send the pulses to some kind of counter, and from the counter, you get the intensity. So theoretically, and you can actually count a single pulse. Now, there's something in addition to being solar blind, there's something very important about the silicon carbide, because it's a wide bandgap semiconductor. Since it's a wide bandgap semiconductor, the equilibrium concentration of electron hole pairs is essentially negligible. So it doesn't hardly exist. The semiconductor people out there call that the intrinsic concentration, the Ni. Well, that number, in silicon carbide is virtually zero. So that number is the quantity or the characteristic that leads to a lot of the dark current. So since there's so few equilibrium electrons and holes floating around in silicon carbide because the band gap is so large, the dark current is virtually non-existent. So as a result of that, you have very little noise, and you can essentially detect, if engineered properly, you can detect a single photon. Okay, so of course it's not that easy. So how do we do this? Well, first you have to design the device. And how do you design the device? Well, we do a lot of computation first, where we design things like doping profiles and things like that. And in order to do that, we've developed a lot of in-house computational tools. And this is an example of a computational tool where you solve the basic semiconductor equations. The basic semiconductor equations are sort of analogous to for semiconductors are sort of analogous to Maxwell's equations for E&M, Schrodinger equation for quantum. And so here's a basic semiconductor equations, and what we do with this is, given a geometry, doping profile, and things like that, given photon flux, we then, we design the device in order to maximize the output current. Okay, and you can see over here that you have a specific doping profile, and over here we have this very large field, and that's one specific region. So we'll channel the electron hole pairs into that region, and then that's where avalanching. Some of the avalanching will be maximized. Okay, so here's oops. Okay, so here's an example of some output. Okay, so what we have is here is a modeling of different doping profiles, what kind of response we have. What this is the gain for a given bias, a reverse bias, and a given input flux of photons. You'll have a a different set of avalanching. So we call that, the gain. So here the gain goes from, we start off with one electron hole pair, one photon coming in, and then we have a gain of 1,000, depending on the structure and the geometry and the reverse bias of the device. So here is there's a model that's produced from our simulations, and here's experimental results that essentially correlate with this. So this particular simulation is corresponding to this set of data here. Okay, so one thing I'd like to point out is if you run this in this avalanche mode, in a sense, it sort of behaves like it can do the job of a channel plate, a multiplier tube. That's a goal actually. We know the channel plate multiplier tubes are they have very low noise, et cetera, but actually the issue is you have to put a pretty high voltage across them, and I guess up into the thousands of volts, and they're also pretty big. Here you have a photodiode. You don't have to put as many volts across it, maybe 80, 100, something like that, 200. And at the same time, it's on micron scale. So you've really drastically reduced the size of a device. And then you're able to hopefully obtain the same kind of results from it. And you can therefore put it in a small satellite or a CubeSat or something like that. Okay, so this sort of gives you some idea of how we're doing this. What we represent here is a bunch of processing steps. You start off with a specialized wafer that has several epitaxial layers on it. We do some patterning, we do some etching. We have to do some special beveling in order to sort of make these sort of photodiode islands. We have to then taper the doping profile. And we do that. First, we do a simulation of what kind of doping profile we'll want, and then we'll do a simulation of the ion implantation, and that will sort of get us, sort of going in order to achieve the actually detailed characteristics we want in order to get the gain we want. Okay, so that was, the previous was a cartoon. These are actually micrographs of certain parts of the process. Well, the process essentially starts off with patterning and then an etching away to isolate where you're going to put the photodiodes on the chip, on the die. Then eventually you etch away and you start beveling different sides, isolate the photodiodes, do some oxidation. Essentially try to passivate the surfaces, remove unwanted traps, put on anti-reflective coatings, do some metallizations, do some contacts, and eventually you get an array of photodiodes or avalanche photodiodes. And here is a micrograph of zooming in on some of them. This distance here is about 200 microns, and here is the full array of the finished diodes. So essentially these diodes, well fabricated, and at this point we have established this process pretty well. So they're easily reproducible, and what we're trying to do next is essentially start making these or start putting the associated readout electronics. So our next goal, we've essentially established the process. It's reliable. It works well. Our next goal now is to put in the readout electronics and then put them into an array so we can even perhaps get into either a single detector that detects UV photons from some source that NASA or other entities are interested in, or have an array that will then image that source. Okay, so here's some results. Okay, so another picture of a different photodetector. This time it's bonded. Here are the results of just the IV characteristics. And what we have here are certain IV characteristics. This is at low voltage, this is high voltage, this is the log. I can't see it from here, but I think it's the log of the current. And what we have is a different wavelength illumination. And it's on a log scale, so the separation is actually pretty large between curves. And so we have here that's the dark current. Then we have 200 nanometers, 300 and 400 nanometer light. Okay, and if we get past the 400 nanometer, it will go down again because of the visible blind. Okay, so with the transparency for the visible. So then one of the key points of this is you see this as avalanching point on the high voltage. So what you do is you bias this near breakdown. So if a single photon comes in, it'll kick up the avalanche, and then you'll be able to, from that single photon, produce current pulses, and then be able to detect the single UV photons. I don't know what's, okay. So commercial technology, status and next steps. Okay, so what have we done so far? Well, we've made this, we've established the process. At this point, we want to step up. We want to, turn this into more of a. We need to package. We need to perfect the contacts, and essentially we need to go into. I wouldn't say at a production level, but like a first stage or a small prototype production where you get a wafer. You pattern the entire wafer. There's some kind of stepper and we go from essentially going from the chip level or the die level of one at a time to the wafer level. And once we are able to do that, we can, to a certain extent, have a small mass production process because we can probably get about 100 chips, 100 photodiodes of APDs off of a wafer. Okay, so why should NASA be interested in this? And what I guess for one thing, and again, let me just point out the cost of this wouldn't be that high of transferring to the next. So we actually have some proposals in to take it to this next stage, and hopefully, that we will, obtain those resources and be able to go to this next stage. But this is real doable, and for, relatively speaking, not that high a cost. Okay, and generally, okay, why would the government or other NASA or other agencies invest? It's based on this new wideband semiconductor capabilities. It allows for the realization of next generation UV spectroscopy, much smaller scale, same results, and also power electronics. It allows for much more efficient and lighter weight electronics and instrumentation. That's the whole idea. The driving factor, one of the major driving factors behind the silicon carbide technology is that can reduce, because it's this wide band gap allows it to hold off a lot of voltage, so it can reduce the size of high voltage systems to the micron scale level. And in addition to NASA, DOD, Department of Energy, and healthcare, manufacturing, applications on all these areas. Okay, so again, I'm trying to advance this. Okay, so what are the applications? Well, NASA applications, again, in deep UV spectroscopy, and in addition, this can also function as an ion detector. So another direction that we'd like to go on this is now that we've developed this UV detector, an ion comes in and again creates electron hole pairs, and again we can essentially apply virtually the same system to detect ions, protons most likely, or maybe heavier ions. Okay, and then the DOD, early warning, anything that you need to detect UV, early warning systems for rockets and things like that, and especially since this is low noise. Since it's low noise, it can detect like single photons. You don't need very bright sources. And of course, then we get into public health. UV exposure for individuals causes skin cancer and things like that. You want to avoid that. Then on the other end of that, we have sanitation. UV is really, people use UV for sanitation in operating rooms, kitchen, and things, et cetera. On the other end of the emitters of UV, you really want to detect them as well, making sure you're putting out the right things. Then finally, in manufacturing, UV imaging, you can detect obviously much smaller wavelength. You can detect things, defects and things like that, that you cannot see with visible light. And so so if you're looking for, you're wanting to make beautiful surfaces, et cetera, defect-free, no cracks, you can use UV cameras to detect those defects. And then finally, of course, we need UV detection for climate change, ozone layer emissions, hydrogen emissions, all these kinds of, spectroscopy. Okay, next. So what do we do? Okay, getting back to what's happening at the company that's making this, at CoolCat Electronics. Well, we have the facilities to make. We've been making these. We've organized over the past, let's say, 5 years. We've developed a pretty good system, a whole bunch of in-house processing capabilities, and also we are in close proximity to the University of Maryland, where we've had an arrangement, of course, where we can rent space and at their state-of-the-art fab facility. And so between the in-house processing capabilities and the fab at the University of Maryland, we can make a lot of great stuff, actually. Virtually anything that we sort of put our minds to, we can make. And then, and of course, then at CoolCat itself, we have a really great testing facility, probe stations, cryostats, RF test equipment, high voltage testing, optical, UV, IR, all this kind of thing. So we're pretty well equipped to continue this process, continue developing these products and others. Okay, so. We were also asked to talk about the core competencies of our group. Well, again, this talk was focused on silicon carbide, and in particular, the wideband semiconductor applications of UV, ultraviolet, deep UV photodetectors, and avalanche photodiodes. You can also use silicon carbide for power electronics. So we have a program for wide band gap power electronics as well. New power electronics, in a sense, it's an analogous idea. With silicon carbide, the next generation of power electronics will be able to reduce power converters. Let's say your cell phone your laptop charger from something that's maybe this big to something that's 1/10 the size of this. It's mainly because of this capabilities of the wide band gap allows you to do that. So we expect that to be the power electronics for the 21st century. And the sponsors of our fabrication and power of wide band gap systems, wide band gap devices, is NASA and the Army Research Laboratory. So in addition to fabricating, we also design, and we've developed a lot of design tools, computer-aided design tools, and not just for a specific device, but for silicon carbide-based circuits as well. So we develop models and circuits, actually design capabilities for designing the avalanche photodiodes, and as well as for power electronics. So we have a unique capability of sort of like a SPICE, computer-aided design circuit simulator for silicon carbide-based systems. And then, of course, we're electrical engineers and applied physicists and stuff, so we always dabble in instrumentation and electronics because we build a lot of electronics for these test systems, but we also prototype electronics for outside agencies. Okay, so this is a little bit more of a discussion of our core competencies. Okay, so we said that we deal with photodetectors and sensors. Well, this talk was focused on UV detectors, but we also have a program on IR and long-wave IR and short-wave IR detectors. So this is a antenna-based program on long-wave IR detectors. We also have a germanium-based program on short-wave IR detectors. And so this is about focused on 10 microns. We have another program with DARPA focused on about 1.5, 1.6, 1.7 microns. That's an interesting program where we're trying to change the band gap or do some kind of band gap engineering of germanium so we can detect between about 1.6, 1.7, 1.8 microns. And then again, we have our UV program over here with the silicon carbide. Okay, so I also said we have, we do a lot of CAD, computer-aided design development. Well, what we developed, I mentioned that we are developing a unique circuit simulator, SPICE. Okay, so we started developing this SPICE for unique applications. Well, we started with an application for NASA. This was essentially our first program, about where we put a big effort into this, starting around 2010, where we developed a proprietary SPICE, or circuit simulator, for various unique applications. The NASA application specifically, we've begun with cryogenic and radiation-hard environments, developing a SPICE or a computer-aided design circuit simulator for that. And it works. It's a full-fledged simulator. It's you can download this. I should have put the download location. We can download it from our website, which is you just go to the Cool Cat Electronics website, and there's a path to download it. About 7,000 people have downloaded it so far. I don't know how many of those people are using it, but I assume a fair number. And it's being developed quite well for these unique applications. And now we're developing specifically for the silicon carbide applications, where we're doing circuit simulation for silicon carbide, has a specific models for the silicon carbide devices. And then at the same time, it allows for you to calculate thermal applications, because that's very important for power electronics. Okay, so I think I'm good. And here is some instrumentation that we developed for, one thing that's over here is a commercial application of our UV detectors, where we've made a bracelet. And we put the UV detector in the bracelet, and that's called Sun Friend. And we're partnering with another company, and they did the design. And what you're supposed to do is you put the UV detectors here, and you're supposed to wear that like at the beach or something like that to make sure that you're not getting too burnt up in the sun. So I think I'll stop there. I think I've talked a little too much, but we have about 2 minutes left for questions. Thank you very much for your attention. Questions? Yes, sir.
So you mentioned a little bit about, yield. And so do you have adequate yield to get the sensitivity to do the photon counting, or is that something that you want to tweak up the process on to get improved yield?
It's pretty good, to tell you the truth. There's two things. Well, first of all, the dark, if we just bias this, without any current, without any avalanching, without any light coming in, the dark current is in the order of picoamps, which is pretty good. You're used to silicons because of the wide band gap, so how many photons can we collect, actually count with at this point? Can we actually go down to one? Maybe, actually, because like one of the first slides I showed was the pulses. And it's hard for me to go back, but essentially you have to do, as you said, I have to set a threshold, right? Do you remember? And if a real photon comes in, then you get a high threshold. If the electron hole pair, the pulse is generated by just some noise, the pulses has a much lower amplitude.
Right. But
So
the noise is low enough that you can set the threshold and reliably count.
yes. We're getting to that point. And and the process is repeatable. You know, we're ready for we're ready for the next stage. Actually, it's been a successful, great program. We're very happy with it. Thanks. Thank you. Yes.
Yes, thinking of those things as MCP replacements, what sort of pixel size do you think? How deep in
The pixel is about 200. Well, the element is the radius, the diameter is about 200 microns at this point. It can be larger, smaller. You know, it depends on, you know, the larger it is, the more potential you have for a defect. But you know, 200 at the moment we have 50 micron, 100 micron, 200 micron pixels, and they all seem to be, you know, working pretty well. The dark current is more scaling with the radius than the area. So it's really leakage on the sides that is sort of limiting our resolution, giving rise to the dark current as opposed to the the intrinsic carriers and defects inside the general 2D kind of area. So at this point, I don't, I'm not sure, but I see scaling up to 200, maybe 400, okay. Okay, so that's the next thing that we're working on. Yes. Yes. I cannot remember. But I will talk to you about that. The responsivity, I think I have a graph responsivity, and we've been looking at that more specifically.
So that's how low in the UV can you go? Can you go down to like 100 nanometers sensitivity?
Well, at the moment, the UV, we're about down to 200. I mean, you saw the graph we had was to 200. The issue is, UV generates electron hole pair, and it doesn't penetrate very far, right? It gets absorbed right on the surface. So the question is, can you then separate that electron hole pair at the surface so it doesn't recombine immediately? So at this point, I comfortably say 200, but I think it's real feasible with more engineering of the doping and stuff like that to separate the electron hole pairs at the surface and get it down to below, to below 200. I mean, this is really, a first run. Right. Right. Okay. Well, thanks a lot. Thank you very much.